Right, what we're going to go through now is some more work around calculations of power, active, reactive and apparent power in systems. First thing we're going to look at is how we can deal with power in terms of multiple load systems. This is like where you're any sort of substation system is going to have a number of different motors, banks of heaters connected to it, transformers. It's going to have some power factor correction capacitors and so on, all effectively connected in parallel to that one source of supply. All right. So problems where multiple real and reactive loads are connected to a single source can be solved by simply summing all the individual real and reactive components together, as in this example. So we'll go through this example, and then there are at least one other example in this week's worksheet for you to have a go at. So in this load system, we got a 400 volt supply of AC electricity, and we got connected two resistor banks. Effectively, you could say they're heaters or something. We got 12.5 kilowatts, a 6 kilowatt. We've got a motor that's 13 kilowatts of power and 7 kVAR reactive. And we've got two reactive inductors, one reactive inductor, and we've got a couple of capacitors connected as well. Okay, so if you remember from week one, we consider that reactive loads draw reactive power from that source or supply, so they take reactive power or absorb it. Capacitors are said to give reactive power back to that system. Yeah. So what we're looking at is calculating the overall P, Q and S connected to that system. The real power or active power P in watts, the reactive power Q in VARs, and the apparent power S in VA connected to that system, drawn from that system. What's useful to do is draw one like this spider diagram of that system, because everything's connected to a load center in parallel. And we draw arrows showing the flow of different powers to and from that source. So the inductors have got arrows pointing into them, so are the resistors. The capacitor has got arrows pointing from the capacitor into the system, and a motor's got two arrows because that's got a reactive and an active part to it. It's taken watts and reactive power from the system. Yeah. All okay with that so far? Yeah? So what we're going to do now is calculate the total reactive power drawn from the supply, the total real power or active power drawn from the supply, and the total apparent power drawn from the supply, the line current drawn, and the power factor of the complete system. Okay, so it's fairly simple in terms of the first two bits, because it is all the reactive powers summed. So I'll start at the bottom of this page. Number one, we're looking to find the total reactive power, and it is equal to QL1 plus QL2 plus the Q taken by the motor, QM, take away QC1 and QC2, because we need to consider them as negative because they're given reactive power back to the source. Yeah? We could equally argue that they're negative and the other ones are positive. We'll still end up with the same answer, magnitude-wise. Okay, it'll just have different direction. Depends whether we want to talk about what's being drawn from the source or whether we're talking about what's being given back to the source. Yeah. So that is quite simply, because they're all in K as well, we can just use the numbers and just add them all up. So QL1 is 3.2, L2, we ain't got an L2, yes we have, L1 is 3.5, 3.2 plus the motor is 7 plus minus C1 is 9 minus, I've only got one C, no C2, 1.2. And the answer to that is, anyone with a calculator? Sorry? 3.5 K var. Yeah. Yeah. So, no, I don't. That's just, yeah. But a load centre, like we're talking about, every load is connected in parallel effectively. Any motor, all the motors are effectively connected to the national grid in parallel, aren't they? So everything's effectively in parallel. Just add them all up and end up with an answer. So that's that. Second one is how much PT is. In that particular example, that has to be the power associated with the resistor 1 plus the power associated with resistor 2 plus the power associated with the motor. They're the only three real powers in that system. We've got 2.5 kilowatts plus 6 kilowatts plus 13 kilowatts equals 21.5 kilowatts, I believe. Yeah. All fairly simple stuff so far, but you have to know that it is the sum of all the individual ones, the underlying electrical principle involved. Before we go on to do the next bit, how do I do it? How do I find S? Explain to me a little better than that, Matt.
As the reactive and the square.
So we're going to find the total apparent power, S. This is number 3. Yeah. So what's handy for that type of calculation we've been covering the last couple of weeks? What helps with it, Luke? The power triangle, doesn't it? Because we got this power triangle that we can draw like this. They don't take long to do, and they're really helpful in making sure we get this right. We got 3.5 kvar, and that's our QT. And we've got PT along the horizontal axis that is 21.5 kilowatts. And this is S along here. So you're right, Matt, in what you say. S is the square root of PT squared plus QT squared. That's root 21.5 squared plus 3.5 squared. I think if you push the buttons, and please check because I have been known to get things wrong, 21.78 kVA. Yep, everyone happy with that? So that's simply by adding all the reactive powers up, adding all the real powers up, and then using the power triangle to find the hypotenuse, which is your apparent power, or volt amps. Yep. Right, line current, how are we going to find that? Sorry?
Sorry, you have to transfer electric feed like line.
Yeah, you're going to use the other relationship that would give you S. We know that S is equal to IL, the line current, multiplied by the voltage E. Yeah? And that rearranges to IL is equal to, and that should be ST, IL is equal to ST over E, which is 21,780 over 400 equals. Notice I had to pull it out of the kVars or multiply it by 10 to the 3 to do that calculation, because we've got to be in the same multiple. That come out to, I made it 54.45 amps. Right, all follow that? Yeah. Number 5. Power factor. What's helpful again? Here. What's the power factor equal to? P, which is 21.5 kilowatts. So this triangle is helpful again, isn't it? Q was 3.5 kVAR. S 21.78 kVA. Yeah. Where's the power factor come from here? Yeah. So if we call that angle in there theta, yeah, it's equal to cosine of that angle, and the cosine is equal to? If you can't remember it, adjacent hypotenuse. So it must be PT over S. That's 21.5 over 21.78. I make that 0.987. That's a ratio, that's all it is. Yeah. Okay. Pretty good power factor, that is. Not many systems will come up with a power factor that close to unity. Is that all I asked for in the first place? Yeah, power factor, line current power factor. So that is how you could do multiple load systems. Alright, in the tutorials questions, there's one where I've given you, instead of giving you 7k vars, 13 kilowatts for the motor, I might have given you the power and the power factor or the phase angle. So you've got to do another calculation with the triangle just to find how many vars the motor's taken or something like that. But there's a different angle on the problem, but all uses the same techniques. Yeah? Alright? But yeah, for obvious reasons, we ain't got time to go through multiple examples on the board, but there are examples that use. There's an example in there where you might also again be looking at something we looked at last week. What capacitor could we add to improve the power factor of the system still further? Let's look at the tutorial questions for this week. Take one and pass it around, Danny. Sorry. Question 1 is a multi-load system. Yeah, I've given you the motor ratings on that one in kilowatts and vars. But the second one is another system, and I've given you a motor rated at 5.6 full load current with a power factor of 0.75, and the other motor is rated at 10 amps full load current, power factor is 0.65. So you've got to do some preliminary calculations there just to find out what power, active and reactive powers, are being drawn by those two motors, so that you can draw your spider diagram up. And then us going through the same process as we've just gone through. So there's two questions similar to that one on this week's tutorial sheet. And it's possible that you could get a question like around that area in your exam as well. Alright? Okay, second calculation style bit to this week's session is to go through solving AC circuits using the power triangle method. I reckon we're about halfway through. Do you want a quick coffee? Yeah? Quick coffee? I feel I could do with getting something. Yeah. I'm doing a lot of talking, yeah? So we'll have a quick coffee, and then we've got two more different styles of question to go through. I think that's about right, really.